Okay, so good evening, everyone. So yesterday we just discussed about the studentized bootstrap method. In that method, we discussed about the confidence interval of that particular studentized bootstrap method. That was your theta cap minus t star 1 minus alpha by 2 into estimated standard error. All right, and upper limit was theta cap minus t star alpha by 2 into estimated standard error. Okay, so now we just took the example yesterday about that if we have the n equals to 20 samples we are having and the s square, the estimated standard deviation was given by 156.8, and we use the chi-square distribution in such manner. All right. So how we are going to deal with that one? So in that one, after computing this, we need the chi-square pivotal method, but we are not going to use that one. All right. So instead of that one, chi-square, we are going to use the studentized bootstrap for variance. That is, for that first we just find out the theta cap. That is the our sample standard deviation. All right, that was 1 upon 1 n minus 1 summation I goes to 1 to n xi minus x bar whole square from our given sample, and for that given standard deviation, estimated standard deviation, we are going to compute the approximate standard error, that was s square into square root of 2 into 2 upon n minus 1. So after that we just compute the studentized t statistics, that is t equals to s square minus sigma square upon s square into square root of 2 upon n minus 1. After bootstrapping, after doing the resampling again and again from the given theta cap, we just find out the studentized t statistics again and again for each sample. That will be s b star square minus s square s b star square into square root of 2 upon n minus 1. So for that one we have the R code here. We will discuss this R code. Okay. So here what we are doing for the simulated data, we are going to do it. We just put the set.seed for to generate the same sample from the same seed again and again. Here in this example, we didn't have the sample. They just simply said we had the 20 observation, but they didn't provide us the observation. So what we are doing, we are going to generate those observations from normal distribution with mean 250 and standard deviation 12. All right. N is defined as the length of our sample, and S2 is the variance of our generated sample. That will be our sample variance. After that, we will calculate the standard error. So in that one, standard error from this formula, it was s square into square root of 2 upon n minus 1. So we used the same one. So s2 into square root of 2 upon n minus 1. Right. So we calculate all these things. So this is our random sample from the given data, and then we just check the length of our data set 20. Then we calculated the standard, sample variance that was stored in S2, that is 180 approximate, right? So then we calculate the standard error for the given variance, that is 58.48. So after that, we are going to use the studentized bootstrap. So we are going to repeat it 5,000 times. All right, and T star, our T statistics for bootstrap sampling, we are going to store in the T star in an as a null vector. We are going to define T star as a null vector here. After that, we are going to apply the for loop to generate the resampling again and again up to 1 to 5,000 times. So here boot sample. So we are going to generate the sample from the given S of size n and with replacement, and after that we are going to calculate the variance of each boot sample here in S2 star. In that one we are going to get the variance of each sample with the command var boot underscore sample. With respect to each sample variance, we are going to calculate the standard error that will be stored in SC underscore star. So that was S2 star from here that we calculated into square root of 2 upon n minus 1. Right. With respect to that, we are going to calculate our T statistic. All right. So in that one, it will be S2 star S2 underscore star minus S2, that original variance, sample variance, and the sample variance that we are calculating for each sample through the resampling method, divided by the SC star, means standard error with respect to each resample. Here you may ask that why I am not storing that one standard error and sample variance. We can store sample variance and sample standard error also, but we don't need to show it. All right, if you want to show it, so you can store it also, but we need to finally show the T statistics. So that's why we are not going to store, we are not storing both of them, the sample resampling variance and the resampling standard error. Right, after that we will close the bracket and we will stop the loop. After that we are going to calculate the T lower limit and T upper, and that is quantile T star at the value of alpha 0.025 and quantile T star at the value of alpha, that is 0.975. So here in this formula, when you are having the T star 1 minus alpha by 2 and T star alpha by 2, this is basically the T statistic from your table, T test table, right? So that's why we are going to calculate by the quantile T star. All right. So in that one, the confidence limit will be, we are going to combine S2 minus, that is basically your theta cap minus T upper into the standard error. Okay. With for your estimated standard error that we are going to store here, right? This one SC underscore S2 and S2 minus T lower into SC underscore S2. All right. So after that we will call it through the command cat. Now we are going to use that one. So T star up to T star we calculated. So we will run it. So this is the confidence interval of our variance through the studentized studentized bootstrap method, And similarly, we use the same data and bootstrap samples. So we are going to use it for the percentile and the basic pivotal and through the chi-square. So pivotal and the percentile, I already explained you how to calculate that one. That I'm not going to explain again. Sorry, what happened? In the basic, which bracket is remaining? Unexpected bracket in S2 quantile. Oh, sorry. Let me check this one. Yeah, it's working. So I'm going to calculate for the percentile. Okay, let's check what is the percentile. Okay, sorry. I'm calculating the last only. So the chi-square, we just check the chi-square confidence interval, that is n minus 1 h2 divided by q chi-square 0.975 with n minus 1 degree of freedom from the this formula that we discussed here. Okay, this one. Through this method, we are going to calculate the confidence interval and 2 into h2 minus quantile function of n minus 1 into h2 divided by q chi square 0.025 with n minus 1 degree of freedom. So this will be your final results. Okay, so in the see what is the difference you will find here. What type of error it is showing? Okay, maybe I just uh, CI percentile is not found. Why? Why CI percentile is not found? Quantile, boot variance, I am having. So why quant one bracket? Okay. I just forget the bracket from here. Okay, then one bracket is here, one bracket is here. So one bracket should be here. Yeah. So I forgot to put the one bracket was removed, so that's why this error was there. All right. So now see the difference. Okay, in your bootstrap, that one in your confidence interval by the different methods. So here from the classical chi-square it is 43.83 and upper limit was of the confidence interval is 161.67, while through the percentile it was 28.26. That is quite differ from that one, and the upper limit was 133.51. And for the basic it was 18.06 and upper limit was 123.31, and studentized was 42.79 and upper was 204. So lower limit was quite similar, but upper limit differences we have seen. But here you can see that they are undergoing, or they have the width of the confidence interval is not that much good in compared to the that one studentized. So studentized was much better in compared to the percentile and the basic confidence intervals here. All right. So after that, we will discuss about the bootstrap, double bootstrap for the standard error estimation. All right. So it is very important. Double bootstrap is also known as the nested bootstrap for the standard error estimation. Okay. So the problem is that here why we need it. So when we constructing the bootstrap confidence interval through the through the bootstrap T methods often provide the better coverage accuracy than the simpler methods like percentile and bootstrap. But however, the bootstrap T interval requires an estimation of the standard error of bootstrap replicate the theta cap star, right? So it needs the replicate of that one. So in that one, typically we use a simple formula, the sample standard deviation of the bootstrap distribution. But this estimate is random and may be sometime unstable, because what is happening here, we are going to generate the sample again and again, and for each sample we are calculating the estimated standard error for each sample. So every time the sample is random, so every single time the standard error that we are going to calculate, that will be again a random, and at that in that case it may be unstable, more special, more possibly for the small sample and the for complex statistics like that. We were talking about the variance, or we were talking about the mean, but if we are going to calculate some complex statistic, at that time this one will becomes more complicated. All right, so at that time double bootstrap or the nested bootstrap method uh, address this by using a second, or you can say the inner level of resampling to estimate the standard error for each theta cap star. So this is a more accurate studentized statistics, and consequently confidence interval with the coverage closer to the nominal level. So what is there basically in this one? So in this methods, how this method works, that in that one we have, for each outer sample we need to draw the, again we need to draw the sample. So how it will work, so I just explain you one by one. So suppose we have the sample x, that is x1 x2 up to xn is the sample is given. Okay, that is our original random sample of size n. So and theta is our parameter under the study. All right, theta is our parameter under the study, and we are going to estimate it by the theta x. Sorry, tx. We are going to estimate it. So theta cap is supposed be the estimate of computed that we compute from the original sample. So suppose we have the theta cap as our estimated value. All right. That could be any one, mean, median, or correlation coefficient, or regression coefficient. So in that one, we need to generate two samples. Okay, two bootstrap sample we need to generate. One is called as the outer bootstrap. Okay, in that one, this is denoted by the x star b, small b, and that we are going to drawn with replacement. Okay, from given sample. Okay, from the given original sample x1, x2 up to xn, that we are going to draw. Okay, b number of times. Okay, sorry, small b equals to 1 to up to capital B, that could be any number, say 1000 times, right? and another one is the inner bootstrap that we are going to draw. So inner bootstrap will be, so we are going to generate the another sample x double star c drawn with the replacement again with replacement. Okay, this sample now, this new sample, we need to generate from x star b. Okay, so here c will be 1 to up to capital C. So now, and we need to estimate corresponding that. So corresponding to both samples, we need to corresponding to both samples, we will estimate first theta cap star b, that will be our say t x star b, and theta cap double star c, sorry, not here, in the prefix only, that will be t x double star c. All right, this will be the estimate. So basically what you need to do, if I just say we had the original sample earlier, just understand this one, x1, x2 up to xn, we had earlier this original sample. So with this original sample, we generated the new sample of similar size, that was our x1 star 1, x2 star 1, and so on, x n star 1, and then x2, sorry, x1 star 2, x2 star 2, and so on up to x n star 2, and so on. After that, x1 star capital B, x2 star capital B, and so on up to xn star capital B. That's how we were generating the random sample. Yes or no? Till now, we were generating the sample like this in the bootstrapping. Okay. So now what we need to do after this? Anyone? Okay. So after that, what we need to do? So now again, we were using this as a population. This sample we were using as our mini population, and we were generating this sample. So now what we are going to do? We are going to use this sample. Okay, and we will generate a new sample from this sample, and we will assume this sample as a population, and again we will generate the new sample that will be like this: x1 star 1, x2 star 2, and so on up to xn star star, sorry, it is one only, star 1, and so on up to x1 star capital C, x2 star capital C, and so on up to x n capital star double star C. Here this C that we choose, it can be any number, say equals to 100. So what you need to do, earlier you had the one sample and you assumed it as a population, and from this population you generated the 1,000 samples of same sample size. All right, now what you need to do, you will take this sample and you generate the another c number of samples of same size n. So means here you had the 1,000 samples here. Now you are going to generate the 100 samples again from this one. So this sample will call as the outer and this sample will call as the inner. Okay, and so you need to do it for each sample again. So for this one it will be x1 double star 1, okay, x2 double star 1, and so on up to x and double star 1, and so on up to again x 1 double star c x 2 double star c, and so on up to x and double star c, so on up to for this sample again x1 star sorry x1 double star 1, x2 double star 2, and so on up to x and double star capital C, and so on up to x1 double star 1, x2 double star 2, sorry, C, not 1, C, and up to x, it, it is 1 only, x n double star C. So what you need to do? You need to do for you need to generate the random sample, C random samples for each sample. So what you are doing? You are running a two loops. Means you are going to run a loop inside your existing loop. Okay. So that is called as the nested bootstrap sample. After that, you will compute that estimate corresponding estimate for each one. All right. So after that, what we are going to do after generating this one, all right. And this is also with replacement. This was for with replacement. Okay. And this is again, this one will also again with replacement. Okay. So after that, what we are going to do, we will, after obtaining the inner samples, okay, we will calculate the standard error, estimated standard error for each one. That will be the standard error, standard deviation of theta 1 cap star 1, theta cap double star 2, and so on up to theta cap double star C. All right. This is an estimated standard error of that one. Okay. This is an estimate of the standard error of theta cap star B. All right. For every single one, this is your standard error. So after that, we will compute in the next step. We will compute the T star B. That will be theta cap star B minus theta cap divided by standard error of estimated standard error of star B. All right. So here one situation may occur if the sample size is too small. So one situation may occur, that is the estimated standard error could be 0. So how to overcome this one? And this will be defined as this will be called as undefined. Okay, this situation will call, in this situation, standard error will called as the undefined. How to handle this one, we will talk later. First, we just understand how we are going to do it. So when you are going to calculate this one, so we will repeat these first two steps. Okay, if we just say it, so this is our first step. Okay, this is our first step, that we have the sample and we are estimating the theta cap, and after that we are going to calculate the samples, that is step 2. In that one, after that we are calculating the standard error, that is our step 3, and after that we are calculating the T star B, that is called as the step 4. So after that, again what we are going to do, we are going to repeat it. Okay, repeat steps 2 to 4. Okay, 2 to 4 for all B. All right, 1 to up to capital B times. All right, at that time, after that we will have, okay, we will have a set of T star 1, sorry, T star 2 up to T star B. Okay, now we can compute the quantile after this. Okay, quantile of the bootstrap T distribution we can compute. So we can compute the, in that one. So this will be, we call it as the step 5, and this will be our step 6. So here we will compute the alpha by 2 and 1 minus alpha by 2 quantiles. Okay, so the formula you already know. What is the formula of that one? So the formula for that quantile T star alpha by 2 is basically quantile of your T star B alpha by 2. Okay, and T star 1 minus alpha by 2 will be equals to quantile of T star B. So should be the small bracket, and 1 minus alpha by 2. Okay. So corresponding to that, we will calculate the standard error. In the bootstrap, the standard error will be the standard deviation of the sample. So estimated standard error of theta cap will be equals to standard deviation of theta cap star 1, theta cap star 2, and so on up to theta cap star n. Sorry, B. Okay. So after that, you can calculate the confidence interval here. From the, in the similar way, the confidence interval will be uh, it will be similar. That is theta cap minus T star alpha by 2. Sorry, not alpha by 2. 1 minus alpha by 2. right, into estimated standard error of theta cap, and upper limit will be theta cap minus t star alpha by 2 into estimated error of theta cap. So this will be your confidence interval in the nested or double bootstrap method. Is there any confusion or anything that you want to, any doubt that you have, or should we proceed? Do you have any question till here in this theorem, in this nested bootstrap method? Or should we proceed? Okay. So we will proceed after this. So here, do you remember that I just talked about this one? Undefined standard error, right? So to understand that one, we just take one example here. We just discuss one example. Suppose, okay, before going to the R code of the bootstrap, we just discuss this example. Suppose we have a data set X that is say 2468. This is our sample. So here n is 4, right? So and we want to construct a 95% double bootstrap confidence interval or nested bootstrap confidence interval for the population mean. Okay, for the population mean mu. Okay, so we want to construct a 95% double bootstrap, sorry, bootstrap confidence interval. Okay, for population mean mu. Okay, so how we will do it? So in that one, first we need to take the average, sample average. All right. So what we are going to do in this one? Say theta cap is basically 2 plus 4 plus 6 plus 8, right? Divided by 4. So what is the total? 20 upon 4. So that means 5. 5 is my sample size. Okay. So now we are going to choose the small value of B and C. Okay. So choose B equals to say 3 and C equals to 3. Okay. So B equals to 3 is our outer loop and C equals to 3 is our inner loop. So suppose we are going to take the sample from the given this one. So for outer loop, say B equals to 1, we will draw the sample x1 star 1. So with replacement, if you are going to take the sample from this one, 2468, what are the possible samples? Okay. Suppose if we are going to get a sample of 2668, is it possible to get these samples or not? 2668 is possible or not? Right? Yes. So suppose this is my first sample. In that one, I'm going to use this as a population and I'm going to generate the sample again from this one. Okay. In the inner bootstrap. C equals to 3. So I'm going to use this as a population and I will generate this one. So in that one, if I will take the first sample, that is my x1 star 1, that is suppose 6, 6, 2, 8. This could be my one sample because I'm going to take the with replacement. So this is the sample that can occur, right? So at that time, what will be the mean? All right, 10 plus 12, 22 divided by 4. So what it will be? 5.5. That will be the mean, right? Now suppose I'm going to take another sample C2, right? In that one, suppose I'm going to take the sample again that 8, 2, 2, sorry, 8, 2, 6 and 6. In this manner it can occur. So again the sample mean will be 5.5, and suppose in the third one it is again occurring in such manner 6, 2, 8, 2, sorry 8, 6, 6, 2, 8, 6. This one. So again the sample mean will be 5.5. This is the possibility or not to occur the sample in such manner. The possibility is there or not? Right? Possibility is there. So now I have the three means 5.5. If the mean are same 5.5 for all three, what will be the standard error at that time? If these are my three observations, okay. Now don't think it as a mean, just think it as a observation. So these are the three observations. What is the variability is there? The variance. If I have these three observations, what will be the variance? Variance should be 0. Yes or no? Variance should be 0. If variance is 0, so what will be the standard error? Formula of standard error for the mean is sigma upon under the root n. When sigma is 0, so standard error will be 0. Right? So similarly, if you will take the another sample, okay, for second loop, if you just take the another example, at that time, suppose the second sample that you are going to generate x2 star, that is suppose 4, 4, 8, 2. Okay, because 2, 4, 6, 8 is the sample. So at that time, I am going to take the C1 as 4, 8, 4, 2. All right. So what will be the mean at that time? 10 plus 8, 18. So 4.5 will be the mean. 18 by 4, that is 4.5. And suppose I'm going to take the another sample, that is 2, 4, 4, 8. So what will be the mean? Again, it will be 4.5. And the third sample that I am going to take, it is suppose 8, 2, 4, 4. So what will be the mean at that time? Again 4.5. Right. So what is the standard error at that time? Again, standard error will be 0. Right. So similarly for the third one, we can see that if I'm going to take the with the replacement I'm saying, so my x3 can be 888. If this is the possibility or not? Is this possible or not when I'm going to take the sample with replacement? Right. Yes, it is possible. So what I'm going to do in that one, whatever the C1, C2, C3 I will take for all CIs. Okay, for all CIs, the mean will be 8 only, and at that time standard error will be 0. So possibility is there. So in that one, all permutation still give the standard error 0. Okay, so standard error, estimated standard error. Okay, for all three, it is 0. That means it is undefined. Because what happens when you will put this standard error here? Okay, estimated standard error theta cap star b minus theta cap divided by the standard error, estimated standard error of theta cap. It will be undefined because standard error is in the denominator. Yes or no? Right. So after that, all t star will be all t star b will be undefined in that situation. Okay. So this is the practical problem with the small samples and the mean. So the in the inner bootstrap, often we see that the sample values, if the outer samples has little variability, in such cases the double bootstrap fails to produce the usable quantiles. So in that is why we need a large original sample and a large C. Okay, large replications to avoid such a degenerated inner standard error situation. Okay, so that's why we are choosing b equals to 1000 and c equals to 100. All right. So in that one basically, so outer loop should be around in that situation. Outer loop b should be around 1000 to 5000. Okay, first of all, and because the larger b reduce the Monte Carlo error in the quantiles, and inner loop c should be between 50 to 200. You can increase it more than 200. You can increase, or more than 5000. You can increase the outer loop. So increasing the c will improve the estimated of standard error. But with that one in that one it will remove you should remove the some standard error that produce the 0 at that time. So even though you are going to remove some c, you are going to remove some ci, for them standard error is 0, still you will have some CIs will remain for you. Okay, where standard error will not 0. But because we were taking the only 3 sample size, because these 3 possibilities are there. Okay, so if we removed all these 3 possibilities and we just took the only those samples where we have the different sample means, so at that time some standard error will occur and we can estimate the standard error. Okay, so when standard error is 0, T star will be undefined, and this can happen if the statistic is constant over the inner bootstrap. Alright, for example, the mean when the outer sample has the all equal values, or the median with the small discrete samples. So in that one, what are the options we have? First thing is that discard such B and reduce the B accordingly. Alright. Second thing is that set the T star B to a large positive or negative numbers, means for example plus infinity to minus infinity. That is not recommended as it stored the quantiles. Or another point is that increase the C to reduce the chance of zero variance. All right, and the last point is that use a different statistic or smooth bootstrap. All right, so in that in the real life situation or in the practice, when we just go for that one, for sufficient large n and a continuous statistic in that one, zero inner standard error is very rare, but sometimes it may happen. All right. So when we should use the double bootstrap? So when the standard error bootstrap T performs poorly, for example, for the skewed distribution or small samples or non-smooth statistics like quantile. Second, we can use it when we need to improve the coverage accuracy, because when you are going to use the double one, so what is happening at that time? If B is 1000, suppose, and C is 100, so how many samples you have? Basically, you have the samples B into C, that is 100,000 samples you have. Okay, so that is a very large number. Okay, so at that time it may take the time, it will become complicated, but it will improve the coverage accuracy. Okay, and the thing, another thing is that for that one you should have enough computational resources. Means your system uh, should have the enough large computational skill. Means like the RAM or the RAM of your that one computer, or the that what we call it, basically the RAM should be very high. Means if you the RAM of your desktop or laptop is 4 GB or 8 GB, it will not work. You need at least 16 GB RAM to produce such a long or such difficult complex programming. All right, so that is the basic double or nested bootstrap method for you. All right, so now we will discuss about the R code of bootstrap. Do you have any doubt in this one, or should we proceed? Should we proceed with this one, with the R code? Okay, so we will proceed with the R code now. So here we are defining the double boots confidence interval function for the for a simulation study. All right. So in that one, we are defining a function of x and statistics. Okay, whatever the statistic we are going to use, mean, median, correlation coefficient, variance. All right, and after that we are going to define b equals to 1000 and c equals to 100. So means again we are going to take the 100,000 samples. All right, so it will start here. X is the original data set or data sample. Okay, and n is the size of that sample. In the statistic, that is the function that computes the statistic of our interest from the sample data set, like mean, median. Okay, after that we are going to define the outer bootstrap for the standard error of theta cap. All right, so here in the B is the number of outer bootstrap replicates. All right, and C is the number of inner bootstrap one. And as I told you, after that, in the replicate B, all right, we repeat the expression inside the B. Okay, inside the capital B, inside the capital B times, and return the results as a vector of our outer theta. And in that one, SC hat, we are going to calculate the standard error of the our outer theta. All right. After that, we are having the T star. Okay, in the supply 1 to B function of B. All right. So here in that one, in the X star, we are having, so basically supply, this supply 1 to B, we are applying the inner function for each integer sample for 1 to B. all right, for each sample that we are resampling, and the result will be a vector or a list of the values that will return by the inner function. Okay, so here we will compute the studentized statistic for each outer bootstrap. So this one is our T star. That T star is basically studentized bootstrap statistic, that is theta star minus theta hat divided by the standard error of theta star. So inside that one T star, we are having the supply. So first we need to compute the S star, that will be the sample. Okay, compute the statistics on the outer bootstrap sample, that is your theta cap star B. And after that we have the inner bootstrap error. So in the inner bootstrap, what we are going to do, we are going to take the sample here. Okay, here we have the take the sample from the original data set, that is X, and for that respect to every that one we are going to compute the theta star, and after that we are going to run the inner bootstrap for standard error of theta star. So in that one we will replicate it C times, and statistics we will compute from the sample X star, and we will generate the sample of size n, all right, with replacement, and we will compute the theta double star 1, theta double star 2 up to theta double star C. All right, so in that SC underscore star we will calculate the standard error of our inner estimates of theta, that is basically theta cap star B. So after that we need to avoid the zero. As we have seen, the zero was occurring in our example that we took. So if standard error of the inner statistic is 0, it should return NA. Otherwise, it should take theta star, theta underscore star minus theta hat divided by the standard error underscore star. All right. And then we will compute it. And theta star we will compute through this formula. And after that, we have the quantile of the bootstrap t distribution. In that one, we are going to compute the quantile, that will be t star c for alpha's value 0.025 and 0.975. Okay, here we are using the na.rm because na can occur in the standard error, so we are going to use na.rm equals to true to ignore the any na value that might have been inserted due to the zero inner standard errors. So after that we will call the confidence interval. Okay, we will construct the confidence interval, that will be theta hat minus t underscore q of the second value, because this tq will generate the two values, so we need the second value of that one for 0.975 into the standard error, estimated standard error, and the second upper limit of the confidence interval will be theta underscore hat minus t underscore q of the first value of t underscore q of this observation into the estimated standard error. Okay, and we are giving the name to C confidence interval, that is 2.5% and 97.5%, and we are going to return the values here. Okay, after that, for example, we are going to generate a sample X of size 50 with mean 5 and standard deviation 2. All right, and we define the statistics as the function of data is the basically the mean of that data. All right, and after that we compute the double bootstrap confidence interval here. So it will be X in the double boot CI. X is the data and statistic is the mean of the data. and B is 500 and C is 50 we are taking. Okay, instead of 1000 and 100. So we just check here because it will run a number of times. So now, because we took the mean 5, so the confidence interval for that one is 4.56 to 5.63. Okay, that will be your R program or R code for your that one double or nested bootstrap method. Okay, do you have any doubt in this one, or should we proceed? Should we proceed? Okay, so we'll proceed there. Now after this, we have the when student type bootstrap method is needed, or it will work much better. Okay, so it will work in a better way when you are going to calculate the ratio, okay, of means. And the challenge in the bootstrap is always, all right, for the skewness. Okay, if it is highly skewed, so the sample distribution of R, the ratio is typically skewed, especially when Y bar is very small, okay, or it's a variable um, continuously varying. And second is the variance depends on the mean. All right. If variance depends on the population mean and the variance of x and y, so the scale of the estimators changes with the unknown parameter. So heteroscedasticity or the known constant variance will be there. And the second one is the percentile bootstrap can have the poor average. So at that time, if y bar is closer to the zero, some bootstrap samples blow up. So the percentile bootstrap simply takes the quantile of R star B, okay, of R star B, because the distribution is skewed and the scale depends on the unknowns. So the percentile interval often under or over cover the studentization, okay. So that's why it is not that much good to use. So general rule is that to use the studentized bootstrap method, that first the statistics has the non-constant variance and the second is the sampling distribution is skewed. So at that time we can use that one studentized bootstrap method. So this is the summary of your bootstrap studentized bootstrap. This is basically the studentization make a pivot distribution more stable, and bootstrap the standardized quant, uh, quantity of t, that is theta, t equals to theta cap minus theta standard estimated of the standard error, and it will achieve the second order accuracy. Okay, this is called as the order of n raised to the power minus 1 is called as the second order accuracy. That is very good because it will in that one your the error or the accuracy will increase exponentially. All right. So, and that requires the standard error estimation for each bootstrap sample. All right. So here you have the better coverage probability and more computation you need to and better it will handle the skewness and it will stabilize the variance. But in that one, you need the more computation. you need standard error formula and can be unstable if the standard error is poorly estimated. As I showed you, if standard error is 0, it will become that one undefined. Okay. So the next thing that we are going to do, that is apply the bootstrap method to the linear regression models. Okay. So this is done. So this is, now we will talk about the bootstrap methods in regression analysis and the hypothesis testing. Okay. So when we just talk about the linear regression, okay, what are the assumptions for the linear regression? When we just go for the linear regression model, what are the assumptions for that one? Okay. So we just discussed here. So suppose we have the model, linear regression model, that is yi equals to beta naught plus beta 1 x1 I, okay, or xi1 plus beta 2 xi2 and up to plus beta p xip plus epsilon I goes to 1 to up to n. This is your multiple linear regression model, right? So what are the assumptions is there when you are going to find out the ordinary least square estimates? If you are going to apply the ordinary least square inference, what are the assumptions? The first assumption is that the errors are normal. That means the epsilon I is IID, normal distribution with mean 0 and variance sigma square, right? Second thing is that data should be homogeneous, means homoscedasticity will be there, means homoscedasticity will be there in the data, means variance of epsilon I is constant, right, for all I. It should remain same, sigma square. Second thing is that independence, third one will be independence, means the errors are independent, right? That means no serial correlation and no clustering. All right. And what should be the fourth one? It should be linearity in the parameter. Okay. Fourth one is that linearity in parameters. Okay. No important omitted variables should be there. All right. So under this assumption, we get the exact finite sample distribution for ordinary least square estimates like t-test or our exact confidence interval. Okay. And asymptotic normality. We can get it. right? That is the thing in the linear regression, right? So after that, if suppose assumptions fails, these assumptions fail, and ordinary least square point estimates may be still unbiased. Okay, in some cases it has been seen that even though the assumptions are going to be failed, the ordinary least square estimates or ordinary least square point estimates may be unbiased, but the other inferences like standard error, confidence interval, and p-values of the t statistics can be wrong in that situation if these assumptions are going to be failed. Okay, if these four assumptions are going to be failed, so at that time point estimation may be correct or unbiased, not correct basically, but unbiased, but the other inferences, standard error, confidence interval, p-values of t statistics may be wrong, and it may be happening because of the sampling distribution of beta cap. Okay, the sampling distribution of beta cap. All right, because what is the assumption with respect to the beta? What are the assumptions with respect to the beta that we have when we are studying the linear regression model? What are the errors? Sorry, what is the distribution of beta that we assume? We assume the normality, right? For the beta also, beta cap. But what happens if beta cap is skewed or heavy tailed? Okay, if beta cap, okay, or the sampling distribution, the sampling distribution of beta cap is skewed and heavy tailed. So at that time, the 95% confidence interval that we find out for beta i's in our regression model, okay, that always we find out usually based on the assumption of asymptotic normality. Okay, so we calculate the confidence intervals of beta i's based on the assumption of asymptotic normality. All right, based on this assumption we find out. So if we are going to use the assumption of the asymptotic normality, even though if it is skewed or heavy tail, so at that time what will happen? So this confidence interval will be either under will be either undercover or overcover. Okay, because it is skewed and heavy tail, right? So, and second thing is that the heteroscedasticity is there in the second condition will be the heteroscedasticity is present, means non-constant variance. Non-constant variance of error, or you will call it as heteroscedasticity. Sorry. Okay, heteroscedasticity there. All right. So at that time, what will happen if variance sigma I is not constant? It will vary with respect to I. Okay. So at that time, usual ordinary least square standard errors will be inconsistent, and what it will take, the test size will be wrong. Okay, and the robust standard errors help out may be unreliable in the small samples. And the second thing is that a dependency, the serial or the clustered. Okay, if the dependency is there and clusters are there, so standard errors that ignore the dependency are too small or false positive. And model misspecification may be happen, so resampling the residuals may be misleading because residuals reflect a wrong model. All right, so that may be happen here. As we have discussed, the standard error may be incorrect. Okay, standard error may be incorrect, confidence interval may have the wrong coverage, and hypothesis test may have the wrong size. All right, so Bootstrap provides the valid inference without assuming the normality of the errors here. Okay, so how can you approach the Bootstrap regression? You can approach the Bootstrap regression in two different manners. First is the paired bootstrapping or case resampling, and second is the residual bootstrapping, that is basically called as the residual resampling. Okay, in that one, paired one, resample xi and yi pairs more robust work with the heteroscedasticity, or in the residual it is resampling residuals epsilon I cap, that will be more efficient and assume the homoscedasticity. All right, so in that one we have the case resampling, that is basically paired bootstrapping. All right, so how it is procedure that paired case bootstrap, in the paired case bootstrap, we basically procedure is that repeatedly resample with replacement the observed pair xi and vi for each bootstrap sample, fit the regression model. Okay, and store the beta I cap. Okay, so means model is there yi beta naught plus beta 1 xi plus epsilon. So we will generate that, and we have the data, that is pairs of x1 y1 x2 y2 up to xn yn. We will fit the original regression and we compute the beta cap and beta cap 1. And after that, what we are going to do, we are going to generate the sample with replacement in the pair xi yi, and we fit the regression model for each sample. All right, and at that time we compute the beta cap star b for each sample, and we will use these beta cap star 1, beta cap star 2 up to beta cap star capital B to find out the that one, our inferences. All right, that is your bootstrap for case paired. In that one, what is that assumption that we have? The assumption is that we treat the joint distribution of x and y as the object that is going to being sampled. Okay, it will be good when the model may be misspecified, means non-linearity is there or heteroscedasticity is there, or when predictors are random, means your xi's are random. At that time it can be used. It is safe because when the predictors are random and the model is form is in the doubt. Okay, after that we have, what are the that one properties of this one. The advantage is model free, so no assumption about the error distribution you need, because what we are doing here, we are generating x1 y1 x2 y2, okay, from the given model. So we are not going to take any assumption about this epsilon I. Handles the heteroscedasticity, means variance can depends on the x that we are going to generate. Random x valid when x is stochastic, and robust works even with the model misspecification. So disadvantage is there. the higher variance than residual bootstrap. So it may have the higher variance in compared to the residual bootstrap, and x distributions change. So each bootstrap has the different x values. So at that time, the distribution of x can be changed. So leverage points, so high leverage points may dominate the some samples. So that may also happen in that one. All right. That is the one thing is that, and after that we have the residual one. In that one, we are going to do, we are going to assume the epsilon, the error, and we just generate the error again and again. Okay. So what we are going to do in this one, we will fit the model once to get the beta I, okay, beta naught cap and beta 1 cap, and residual epsilon I cap. We will compute from the yi minus yi cap. All right. And then we will resample the epsilon I star, usually with replacement as we have done earlier, and then we just compute the again yi star equals to xi dash beta cap yi star equals to xi dash beta cap plus epsilon I cap star. Okay, and we refit the model to xi and yi star. Okay, and collect the beta I cap. Beta cap star I. Okay. In that one, we assume that model is correctly specified, means model is in the linear, okay, linear in the parameters, and errors are IID, identically independently distributed, means it is exchangeable. Okay, we can exchange the error for each sample, and predicted values xi are fixed, okay, or conditioning on the model designing. Okay, so we use it when the model is linear model is we assume that it is correct and problem is non-normal. Okay, but homozygosity and the independence hold. Okay, so we are assuming here that the error that we are assuming epsilon that we are assuming normally distributed with mean 0 and sigma square. So this is not normally distributed, but this is it is following the independence property, and it is following the property of homozygosity. Okay. These two assumptions it should follow, but it should not follow the distribution normal. Okay, it may change, it may have the different model. And then we have other models also, but we are going to talk about these two models. So I just give you the highlight of the other models. That is the, what are the other models we have here in that one. First model that we have, that is the wild. Okay, wild bootstrap we have. Okay, in this procedure, it is similar to the residual bootstrap, but instead of resampling residual, we multiply each residual by the random variable vi with mean 0 and variance 1. Okay, there are two distributions here that we assume for that one. That is basically the Dempster distribution that takes the only two values plus 1 minus 1 with probability 1 by 2. Okay, and another distribution that we assume here, that is mean distribution. Okay, these two distribution we assume for and what we do, we had the model that is y I equals to xi dash beta plus epsilon. So what we are going to do, instead of replacing this epsilon I with the estimated value epsilon I cap, what we are going to do, we are going to introduce a new model that is yi star equals to xi cap, so xi dash beta cap plus epsilon I cap into vi. Here we assume that vi follows these two distributions. Okay, any one of these two. Okay, the Dimchar or Mamin distribution. I will discuss them in the detail later when we will go there. Okay, so what is the assumption regarding this method is that the assumption of heteroscedasticity, that this model is designed for the heteroscedasticity errors. Okay, and it assumes that uh, so here two things is that first thing is basically we say first is it is not homoscedastic, it is heteroscedastic. Second assumption that is uh, errors are not assumed to be identically distributed. These two assumptions we follow in the wild bootstrap method. Okay, so we basically use it in the heteroscedastic regression, and heteroscedastic regression basically we mostly use in the econometrics. Okay, econometrics we use that one. And another method that we have, the parametric bootstrap, that we already discussed earlier. In that one, what we assume that we assume the parameter uh, second is the parametric bootstrap. Okay, in that one we assume that the assume a parametric form of the error, either normal or student t. Okay, and we fit the model to get the beta cap and sigma cap and simulate the standard error and for assumed distribution. Okay, and then we resample again and again. Okay, so basically what is that character we are going to assume the correct estimator, oh sorry, correct distribution. Here we assume a correct distribution of error. Okay, so we use it when parametric is possible and we want to leverage that structure. So at that time we use this one, and after that we have the two more bootstrap methods is there. First is uh, that we should say third one, that is cluster bootstrap method that we use for the cluster or type series data. So what we do, we just resample the clusters or the blocks instead of the individual observations. All right. So at that time we use the cluster bootstrap method. And fourth one is the studentized bootstrap that we have discussed, that bootstrap distribution of the studentized statistics that we we discussed in the previous lecture. Okay, that was studentized bootstrap method. Okay, so these are the methods that we basically use in that one, in the bootstrap regression modeling. So, do you have any doubt till now, or should we proceed? Or we do one thing, bootstrap is there. So, okay, so we do one thing. We just discuss the bootstrap in the detail with the methodology in the next lecture, if you don't have the problem. We will stop here because time is going to be up and we will not able to discuss the entire method today. So should we discuss in the next lecture? Yeah, so we will discuss in the next week in this one. Okay, so there is one thing that I